Hi folks, here is the video for 4.10 and my hope is that it will have sound for the entire time. All right, so 4.10 is all about something called antiderivatives. And I kind of hinted at this during class today, but I do want to make it really clear that this section officially marks the sort of second half of calculus. Okay, so antiderivatives marks the second half of Calc 1. All right, and in particular, what we're going to be doing is figuring out, well, we know how to find all these derivatives. How the heck do we go backwards? All right. And so I do want to take a moment and kind of summarize where we've been so far. All right. And so what do we know so far? We know that we've talked so much about slope, right? Slope has been the central theme for the first half of our class. And in particular, we've looked at average rate of change, and we've looked at instantaneous rate of change. All right, and our average rate of change was the slope of the secant line, and the instantaneous rate of change is the slope of the tangent line. You folks have done so well distinguishing between those two. I do want to say I'm really proud of you for how well you've embraced the concepts here, okay? Now, even though we started by talking about average rate of change, we've actually spent most of our time talking about the instantaneous rate of change, right? And in particular, we said another way of finding these was using derivatives. All right. And so with our derivatives, we learned so many rules, right? We learned the power rule. We learned the product rule. We learned the quotient rule. We learned all the trig derivatives, the exponentials and logs. We learned the derivatives of inverse functions. We learned the derivatives using chain rule. We learned derivatives using implicit differentiation. Right? We learned so many of these rules. And so this is a really good moment if you're like, I have not been feeling very confident on all of these, is to make sure that you have most of this, I'm going to say memorized. And I'm going to put that in quotations because I know for some of us, memorizing things is harder than other people, all right? But I think it's important to think about how far you plan to go in your calculus career or your math career. If you plan to take more classes, especially Calc 2, even if Calc 2 is the end of the road for you, knowing these rules and having them actually memorized will make your life so much easier, okay? Same thing, if you're going to be going to Calc 3, these rules are going to come up again. If you're going to go on to take differential equations, these rules are going to come up again. And there's going to be a lot less time to be like, oh, wait, now I have to memorize them because you're going to be learning so much other stuff, okay? So I would encourage you to start to move in this direction, especially if you have more math classes to take, okay? All right, so what's new? Well, we are going to change our theme a little bit. Our new theme will be area. And in case you've already taken a look at that approximating area Desmos activity, that's sort of a flavor, a tasting of what we're going to be looking at, right? And the way we're going to look at area, we're going to look at it in 3 clumps. We're going to look at it using geometry. Okay. We are going to use area and look at 2-dimensional shapes, right? Which I'll explain later why that's different from geometry. And the third category is going to be looking at 3-dimensional shapes, right? So if we want a roadmap of where we're heading in this last chunk of class, last chunk of the semester, we're looking at area. We're going to start by looking at geometry. We're going to then move to 2-dimensional shapes that maybe don't have nice formulas. That's why I put it separate from geometry. And then we're going to finish off the summer with a bang with 3-dimensional shapes. Okay. And so for 3-dimensional shapes, maybe we add here that we're actually going to be looking at volume, but we will use area to help us find volume. Okay. Now, the last thing I want to put here is we talked about briefly today that if you have a first function of position and you take the derivative, you end up with velocity. And if you take a second derivative, you'll end up with acceleration. And so, that direction, I think, is quite familiar to us now. But what we're going to be including now is how do we go backwards? If we have acceleration, how do we undo the derivative, or rather take the antiderivative? Because if we do take the antiderivative of acceleration, we get back to velocity. And furthermore, if we take the antiderivative of velocity, we actually get back to position, all right? Now, just like you all spent so much time learning the notation, that's actually going to be the focus for today, all right? We're going to start to use symbols that look like this. So squiggly, and then A of t dt would equal V of t, all right? And similarly, if I have V of t and I squiggly the V of t dt, I will get S of t, or the position, okay? Now, obviously, squiggly is not the formal name for this. This is simply what I call it right now when I happen to be writing it. But this whole chunk right here is what we are looking to cover in the next 3 weeks of our summer session, okay? All right, so let's get started with the concept, all right? So we have this table. We've got a bunch of functions, and my question to you is, let's warm up our brains by finding the derivative, okay? So we start with f of x equals x squared. We're going to be really good about our notation, and I'm going to ask that we write f prime of x equals 2x, all right? I do not want us to just write 2x. I will 100% take off points for that. Maybe not 100 points, but I want us to be really thoughtful about our notation, okay? It's a way that we communicate with others about what we're trying to say. So f prime of x equals 2x, all right? That's the derivative of x squared. What about the derivative of cosine? We want to know that that's negative sine x. What about the derivative of e to the 2x? Well, I'm going to highlight this because I think it's really valuable that we remember we want to use chain rule. So we're going to get 2e to the 2x. All right, what about the derivative of f of x? Well, we have tangent of pi x. A good indicator, again, it's not just x in those parentheses, so we're going to need to use chain rule. And in fact, we will have pi times secant squared of pi x. Okay, so that extra pi is from the chain rule. All right, last but not least, we have a super long function, but it happens to be inside of another function. So once again, we're going to use chain rule, and our f prime of x will be 5, that whole inside function to the 4th times the derivative of the inside, which gives us 6x minus 4 plus cosine x. Okay. Now, as I mentioned a few minutes ago, I said if you're moving on to Calc 2 or Calc 3, these questions should feel pretty quick to you. Okay, like I look at them, I know what I'm supposed to do, and I can do them fairly quickly. If you're not at that point yet, it's okay. You have time to get there. But I just want to set up that expectation of probably what that Calc 2 professor is going to want from you is to have this solid foundation. Okay. All right. So because math is a delightful puzzle, let's switch the order in which we're asking the question. This time, I'm giving you the derivative. So I'm saying, here's a derivative. I want to know where it came from. All right, what was the original function? What was the OG function? How do we get back there? Okay, some of these we can kind of do in our head. Some of these are going to be more placeholders for things that we want to think about as we move into Calc 2, okay? So let's get started with this f prime of x equals 3x squared. Now, if we think about this, I think we've seen this particular function enough that if I have x cubed and I use the power rule, I will end up with 3x squared, okay? And so we have f of x equals x cubed. That is an original function that if I take the derivative, I will also end up with 3x squared. But here's the deal. What if I said this, f of x equals x cubed plus 3? And I asked you to take the derivative. What would you end up with? Pretty sure you would still end up with 3x squared. What if I said, here, let's move these to the same line. What if I said f of x equals x cubed minus pi? And I said, take that derivative. I bet you would end up with 3x squared, right? So all three of these seem like they're possible answers. So this plus 3 and this minus pi, those are constants, right? They're numbers. And so what we actually want to start to say as our original function is we're going to say it's f of x equals the function we know plus some constant. And I don't know what that constant is, but it could be 3, like we had here. It could be negative pi. But since I don't know that particular value, I'm just going to give it a letter C and know that C stands for a number. Okay. So if I say, this is the derivative, what's the original function? I want you to tell me f of x equals x cubed plus C. Okay. In fact, if you leave off the plus C, that's going to be incorrect. And I know you don't want to be incorrect, and I don't want to mark you off for that. So let's make sure that we put that plus C at the end. Okay. All right. Let's take a look at some of these other ones. I think the next two, we hope, are ones that we recognize. If I take a function and I take the derivative, I end up with 1 over x. What was that original function? Well, it came from the natural log of x. All right. Now, just like before, it could be maybe natural log of x minus 2 or natural log of x plus 15. I don't know what those numbers could have been, but I know there might have been a number there. And so when I write my original function, I want to say f of x equals natural log of x plus c. All right, and that plus c will just tell me there might have been a number there. We just have to make a space for it in case that number becomes important to find. All right, we could do the same thing with sine of x. Where did sine of x come from? Well, it came from negative cosine x, but it also could have come from negative cosine x plus 1, or maybe negative cosine of x minus 12, right? I don't know what number could have been at the end. And so we're going to say more accurately that f of x equals negative cosine x plus c. Okay. So when you answer the questions, I don't expect you to write out the ones in the black ink, like what are the possible choices, but rather I expect us to write the one in the blue that says, here's the function plus some number that I'm not sure what it is. Okay. All right, so let's take a look at these last two. All right, I think these last two are a little bit trickier. We will learn how to do this one in our class. All right, this will be something very important called U substitution. All right, but for right now, we're just going to play around with it, see if we can figure out what original function it came from. And then this second one, the one with all a trig and like a product and then addition, this is going to be something you will see in Calc 2 called integration by parts. All right, and you'll see this in 151, not in our 150 class, okay? So let's take a look at this f prime of x equals negative 5 e to the negative 5x. Now, if we think back to some of our other problems, we might recall that if we have something more than x in that exponent, that we're going to need to use chain rule, right? This is a very clear case that we used chain rule to get to this derivative. So what does that mean about the original function? Well, the original function is e to the negative 5x, right? Because if I take that derivative, I'll get that extra negative 5 in the front. But just like all the other ones, it's possible there was some number added or subtracted to the end that we don't know what it is. So we're going to say as a full answer, e to the negative 5x plus c. All right. Now this last one here, all right, we're not going to cover this in our class, but I just wanted to show us that look at what we have here, right? We have some function. Let me call that u. And we have what looks to be like the derivative of that function. And then we also have another function and its derivative here. So v du. Now, I bet we can all recognize this as the product rule, okay? So integration by parts, when you learn that in Calc 2, that is how you're going to undo something that came from a product, okay? For right now, I'll just tell you that this derivative came from the function tangent x times square root of x And then we don't want to forget that plus c. Okay. Again, the last one I wouldn't really worry about, but the first 4 in here, we will spend a lot of time working on. And by the end of the course, we really want to make sure that these things in the first 4 boxes, the first 4 rows, are something that is really accessible for us, okay? All right, so let's talk about some notation, okay? So let's review what we have for derivatives. We've learned a lot of different notation for derivatives. Okay. And so here are some of the ones that we've seen. F prime of x, right? We use that one a lot. Y prime, we use that one. Sometimes we do dy dx. Sometimes we write d dx of f of x, right? And you folks have done a really great job of saying, okay, all these different ways, I'm going to learn them all. I know what they mean. I've even gotten some great questions about like, are these all the same? All right, because every instructor has a different flavor. So what we want to do here is build a strong base where we can navigate between instructors and it's still going to be okay. So the antiderivative. All right, what notation are we going to be using now? Well, we are going to be using that squiggly that we showed you earlier. Okay, that is the primary notation. So there's not that many different ones. It's not like derivatives. There's pretty much just one of them. Okay, so our notation is going to look something like this. We're going to have a squiggly. Okay, we call that the integral symbol. We're going to have a function. And at the end, I'm going to be so picky about this. You better have a dx at the end, okay? And that activity, that approximating area activity, that ties into why we need that dx at the end, okay? But let's label some of these. So this squiggly right here and this dx, right? Together, we call those the integral symbol. So if someone says integral symbol, they mean the squiggly plus the dx at the end. And then this function in here, we actually call this the integrand, all right? So if someone says, what's the integrand? They mean what is the function that you are taking the antiderivative of, okay? All right, so that's the good news. The good news is there's like one symbol that you need to know, all right? And it's different from derivatives because we had so many for derivatives, but we're looking at just this one symbol right here. All right, so now that we've talked about the concept and the notation, let's take a look at some of these rules, okay? And so just like we started with derivatives, we started with the power rule that we used pretty much all the time. There is actually a power rule for integrals or antiderivatives, okay? And so when we take the antiderivative, this is actually what we used when we tried to figure out where in the world 3x squared came from, okay? And so let me show you how this works. Let's use that example, all right? So let's say that the integral of 3x squared dx. All right, so that would be another way of saying the function is 3x squared. I want you to find the antiderivative. All right, So in particular, we can say the function is 3x squared, and what we want to find is the antiderivative, also known as the integral, okay? And so if we look at this rule, right, it seems like it's all based on that letter n. Now I'm going to go ahead and pull this 3 out to the front, and we'll see that in just a little bit, but that leaves just x squared dx. And so now here I can see that n equals 2, all right? N equals 2. And so if I use the rule, that's going to give me 3 times, let's see, some sort of fraction. X to the 2 plus 1, because it's n plus 1, all over n plus 1. And we don't want to forget the plus c, because that c again represents what number could have been there that when we took the derivative, it went to 0. All right, so we've plugged in 2 everywhere we see the n. And now let's simplify. 3 x to the 3rd over 3 plus c. And we can see here that this 3 and that 3 will reduce to 1. And we'll end up with x cubed plus c. So something that we could kind of figure in our heads what that might be, here is a more systematic way of approaching that, all right? And so this power rule for integrals, if you see a power, you can use this power rule, all right? Before I leave that though, I want to make a very big deal out of this tiny, tiny little piece right here. Okay. You can only use the power rule when n is not equal to -1. Okay, you can only use the power rule when n does not equal -1. Okay, and this is so important that instead of waiting until later to tell you why, I'm going to tell you right now why that is the exception. All right, so let's bring this over here. The exception. Well, if I have an integral of x to the -1 dx, another way I could write that is the integral of 1 over x dx. In other words, my function is 1 over x. That's what I got after I took a derivative. So what function did it come from? I think we know from earlier in this lesson that it comes from the natural log of x. All right. This is the reason why we cannot just use the power rule for every single power. -1, that power of -1 is the one and only exception. Okay, it is the one and only exception. All right, so power rule, keep that in your pocket. We'll get a chance to practice that in a little bit, but let's move on to properties of these indefinite integrals. Okay, so it turns out that just like we did with the derivatives, if we add or subtract while we are taking an integral, we can add or subtract the results together, okay? Meaning we can sort of take it piece by piece and then go ahead and add or subtract them all together, right? The other rule is the constant multiple rule, all right? So remember earlier how I had that 3x squared, and I said, I'll talk about this later, but I'm just going to bring the 3 out to the front. That right there is like the k. So k is a number. In that example, it was a 3. And I pulled the 3 out to the front, and then I did the antiderivative. Okay, so the sum and difference rule and the constant multiple rule are very similar to the rules that we have for derivatives. Okay. So with that, let's go ahead and try a bunch of examples. All right, practice, practice, practice. All right, so example 1, I have the integral of 5. All right, and so how else could we write this? If we wanted to see x to a power, we could write this as the integral of 5 times x to the 0 power dx. Okay, now using the constant multiple rule, I can say 5 times the integral of x to the 0 dx. And now I can use this power rule, where basically I take the power and I add a number, right? Because when we took a derivative, we subtracted 1. So to get back to the original, we have to add 1. And then we have to divide by that power. So if I apply that power rule, I'll get 5 times x to the 0 plus 1 over 0 plus 1. Don't forget the plus c. And when we simplify this, we end up with 5x plus c. All right. So the integral or antiderivative of 5 dx is 5x plus c. All right, so let's take a look at example 2. Now, example 2, I don't see a constant, and I don't see a power either. So it might be useful for us, just like we wrote it x to the 0, maybe over here we could write x to the 1. And so this would give us the integral of x to the 1 dx. Now 1 is not negative 1, so we can go ahead and use the power rule. X to the 1 plus 1 over 1 plus 1 plus c. And when we simplify that, we get x squared over 2 plus c. So some people like to write it this way, or some people like to do 1/2 x squared plus c. All right, but either one of these would be fine. All right. So whichever way makes more sense to you, x squared over 2 is equivalent to 1/2 x squared. All right, let's keep moving. Example 3, I see a constant multiple, right? So I'm going to go ahead and bring this 2 out to the front. So 2 times the integral of sine x, sine x dx. And let's think about, where did sine come from? Well, it came from negative cosine, took a derivative of negative cosine, and I end up with sine. Don't forget the plus c. And this we would definitely want to rewrite as negative 2 cosine x plus c. All right, so just bring that negative sign to the front. Otherwise, it might look like 2 minus cosine. Okay. Now, this is a really good example of, like, if you're sitting here scratching your head, like, how did she know that it was going to be negative cosine x? Well, the reason I knew that is because I know my derivatives really well. Okay, so the more you know your derivatives, the easier it is to find your antiderivatives. All right, let's take a look at example 4. It looks like I've got a constant multiple and a power rule. So I'm going to go ahead and bring the 4 out to the front. Integral of x cubed dx. This is going to be 4 times x to the 3 plus 1 over 3 plus 1 plus c. And if I simplify this, I get 4 times x to the 4th over 4. And this, we definitely want to reduce the 4 and the 4. And that will give us x to the 4th plus c. And if we pause for a moment and look back, if I said, what's the derivative of x to the 4th? You would have said 4x cubed, right? And so it's not surprising that if we said, what function did I take a derivative of to get 4x cubed, we get x to the 4th, okay? All right, so there are the first 4 examples on the screen for you. And we're going to take a look at 4 more, all right? So example 5, the integral or negative the integral of 2x. So this, my friends, is a constant multiple. So I'm going to go ahead and keep the negative, but also bring the 2 out to the front. And then I'll have my integral symbol x and that dx to finish the integral symbol. I might even want to put a 1 in the power so I know what I'm plugging in for n in the power rule. And so that's going to give me negative 2 x to the 1 plus 1 over 1 plus 1 plus c. And this gives me negative 2 times x squared over 2. And this is another great example of when we should reduce, right? 2 and 2 reduce to 1. But because of that negative sign, we're going to get negative x squared plus c. Right? So especially in the beginning, I would encourage you to write those powers, especially the ones that are invisible that you're just supposed to know. I would make sure that you have those there. All right. This is a test of how well you know your trig derivatives, right? So if we break this up, it's a very long problem, but I'm going to do 2 things. I'm going to split this into 2 integrals. And at the same time, I'm going to take the 3 and I'm going to bring it out to the front. All right, so 3, the integral of cosine x dx, plus the integral of secant x tangent x dx. Now, one thing I want you to notice here, this 3, it only goes with the cosine. So I have a 3, but only in front of the cosine one. There's no 3 in front of the other one, okay? So what function did you take a derivative of to get cosine? Sine x. And what function did you take a derivative of to get secant x tangent x? Secant. And then don't forget that plus c. Okay. We got 2 last examples here of just computing, and then we'll do an example of something where we actually find the plus c. Okay. So example 7. Looks like I could use the power rule, but just like with derivatives, I better write that without a fraction. Okay, so I need to see x to some power and not in the denominator. Now I can use the power rule. X to the negative 43 plus 1 over negative 43 plus 1 plus c. We want to be really careful now because we've spent an entire 5 weeks taking negative numbers and subtracting 1. But now we want to add 1. So negative 43 plus 1 is negative 42. And on the bottom, I'll also have negative 42. Right? So this might be one version, but I encourage us to go with no negative exponents, and we'll get negative 1 over 42 x to the 42 plus c. Okay. So no more negative exponents. We only use that in between to help us see things. But in general, we want our final answers to be with positive exponents. Okay. All right, last example here. I see a 4, so I'm going to go ahead and pull that 4 out to the front using the constant multiple rule. And this, my friends, we saw very briefly in our derivatives unit. But what function did we take a derivative of to get 1 over x squared plus 1? Well, it was our inverse tangent. Okay, it was our inverse tangent. Now, why would I bring this up? I want to bring this up because especially as we get towards the end of Calc 1, you're going to see a lot of this in Calc 2. And so I don't want you to get there and be like, I don't actually know what was important. I want to try and highlight some of the things that tend to come up a lot. So even if you don't remember them, when they come up again, maybe it'll sound familiar, okay? Now, I did want to point something out. Some people write this as 4 arctan of x plus c, and that is absolutely fine, okay? So if you write this first one, you're good to go. You write the second one, you're good to go. But I do want to make one really important point because I've seen this mistake on quite a few papers. When I say tangent with a -1, it is not this. That -1 does not mean a reciprocal, okay? That -1 means the inverse. And so if you do something like this, all right, you're going to be super, super sad about it because that is not correct, all right? Arctan or inverse tan, both of these are okay, but an inverse is not the same as a reciprocal. All right, so let's get these 4 examples on one page for you. All right, so we've had 8 examples where we kind of practice just taking the antiderivative. And you'll see on the quiz that you get a chance to practice those as well. And we're going to finish up today with something we call an initial value problem. All right, and we'll do one example of those, and then we will be done with 4.10. All right, so initial value problems. All right, this is when you find a number for C. Okay, so I've been telling you, you have to write that plus C on the end, but now we're actually going to be able to find a number to plug in there. Okay, so let's take a look at this question. So in example 9, it says car A is traveling at a rate of 88 feet per second when the brakes are applied. Car B is traveling at a rate of 44 feet per second. Both cars begin decelerating at a constant rate of 15 feet per second squared. Which car stops first, and how many seconds elapse before car A stops, and how many seconds elapse before car B stops? So here's what we're going to do. We're going to start with car A. Okay, we're going to start with car A. And we're actually going to create an equation out of what we have. And I know that's not our favorite, but I promise you it's not so bad, okay? So it says both cars begin decelerating at a constant rate of 15 feet per second squared. So what does that mean? That means that the acceleration of car A is negative 15. Okay, negative 15. Well, I want to know what I can do to start to figure out how long it takes for this car to stop. And so what I'm going to do is I'm going to say, let's find our velocity, okay? And from the very first box at the top, I had said velocity is squiggly symbol a of t dt. And now we know that's the integral of a of t dt. So let's plug in our function, integral of negative 15 dt, and let's integrate, okay? So we see here that we have a constant multiple, so I can bring the negative 15 out to the front. And what's left here, x, oh, not sorry, x, t to the 0 dt. This means that I can use the power rule to find the integral, and I get negative 15 times t to the 0 plus 1 over 0 plus 1 plus c, or negative 15t plus c. Okay, so I've used what we learned in this lesson to say, hey, I know the acceleration, let me find the velocity function. Okay, but here's what I want to do. I want to find c. I want to find a number for c. All right, and it turns out that we have some information here. We have that car A is traveling at a rate of 88 feet per second. And it's doing that speed when the brakes are applied, okay? So what that means is that the velocity at time zero meaning the time we hit the brakes, okay? So at the moment we hit the brakes, what is our velocity? 88 feet per second. So here's what we're going to do. We're going to take our velocity function, v of t equals negative 15t plus c. And everywhere we see a 0, or everywhere we see a t, we're going to put a 0. Okay, so this t will become a 0. And then 88, well, that represents v of t, like the whole velocity. So we're going to substitute that as well. And so we'll get 88 equals negative 15t plus c. And whoops, I forgot to change that t to a 0, right? Negative 15 times 0. And what does that give us? Well, c is going to equal 88. Now, what that means is now I can write this equation, my velocity equation, with instead of negative 15t plus c, I can write negative 15t plus 88. Okay. Now, why is this important? Well, I want to know how many seconds elapse before car A stops. And when car A is stopped, we know that the velocity of car A is 0. That means we can say 0 equals negative 15t plus 88. And if we solve for t, we will know the time at which the car stops moving. Okay. So this is for car A. I want you to try and find car B, all right? Follow the same process for car B, and then you'll be able to figure out which car stops first, okay? So I'll leave that as a little cliffhanger. You're welcome to message me if you want to check your answer, but I'll leave that as a little cliffhanger here, and I look forward to hearing your answers for this, okay? Have a great rest of your day.